All right, so while we start winding things up here, page 299 or 29, yeah, whichever. It's chapter 9, 299. I'm just going to speculate that nobody wants to read aloud.
Shoot, where at? I'll read aloud.
Okay. All right. Who would you rather listen to?
You know what?
I would rather listen to the white version of me over there.
You go, who's that?
Who else is so
Okay. Well, do you know where to stop and take a break to explain this?
No.
Oh, well.
I don't know how to
No
explain it.
offense. No
All
offense.
right.
Put my
You should just choose
readers on.
make
Okay. So when you look at page 298, okay, underneath where it says stoichiometry, okay, it's up in whether that's Hunter Green print or, I don't know. It says stoichiometry comes from the Greek words stoicheia, stoichian, okay. I can pronounce stoichiometry if I couldn't do that. Okay. Stoichion, okay, meaning element, and metron meaning measure, okay? So one of the things that we see happening inside that flask inside, there's a chemical reaction taking place. So what you can presume is that you have this clear liquid that's filled up to the, 200 milliliter mark, I suppose. And then you see that, I suppose, a glass dropper bottle that's putting some materials inside of there. And what can you presume is happening there? Does that look like a chemical reaction? Yes, it does. And there's reasons that we know chemical reactions take place is, you could say, precipitates form, or elements change, or heat is given off. Any one of those examples is an example of a chemical reaction, whether it's a thermal type. I guess I had octane and heptane up there because, as you're aware, we're starting that with the freshmen. And let's see here. Does anyone have any younger? 1, 2?
Younger siblings?
Yeah, that are freshmen. 3, 4. I think that's it then. Who's your younger sibling? Okay. Oh, that's right. Yeah. So with that, does that bring back good memories? Freshman year, starting the periodic table. Of course it does.
Absolutely.
Okay. So one of the things that we're talking about, heptane and octane up on the board. But when you combine C8H18, okay, with oxygen, and you have inside of a carburetor a spark plug that sends a spark into your in your valve, in your combustion chamber of your valve, the piston gets pushed down and carbon dioxide is given off. And how would we know without going any further that a chemical reaction has taken place? Because what goes in is octane, C8H18, but what actually comes out of there? Two things. In all combustion reactions, that's one, and carbon dioxide. So we know that a chemical reaction is taking place. Another reason that we would know is that heat is given off as well. So precipitates form, heat is given off, sometimes light, any one of those is going to be an example of a chemical reaction. So what we see here, when we get in about the middle of this chapter, I don't like, I mean, it's very observable, this chemical reaction. It's just that it's not very beneficial for learning what we want to call limiting reactants, okay? So we know that a chemical reaction is taking place because we have two clear fluids. And once you drop one into the other, we see lots of yellow paste, if you want to call that, or how would you, it's a precipitate, but would you call that powder, or how would you classify that yellow substance? We'll just say it's a yellow powder because that's what would happen over in the lab when you did your procedures. When something would fall out of the solution, that was called a precipitate. And that's what you see here as well. So that's what this entire chapter deals with, is not only just the chemical reactions that take place, but the mathematics that goes along with it. Okay, page 299. Much of our knowledge of chemistry is based on careful quantitative analysis of substances involved in chemical reactions. Composition stoichiometry, which you studied in chapter 3, what did we do in chapter 3? Long time ago.
Give us a hint.
Okay, if you had, let's say, 15 grams of calcium chloride.
Was it the percentages?
No.
Was it
Convert grams to what? Okay, two-step process, okay? That is composition stoichiometry, where you are calculating the composition of a substance within an entire compound. Now, that got to be a little more advanced when we started doing molar mass problems, because we would take that one step further. What did we say? Calcium chloride. For instance, if we said we got 15 grams of calcium chloride, okay, how many moles would that be? That's one aspect we did. Again, that's composition stoichiometry, okay? So if it was just how many moles is this, we would say for every mole of calcium chloride, we would have, let's see here, 70, 40, approximately 111 grams of calcium chloride, okay? So that's where we would stop, okay? And then in chapter 7, we took that one step further. Like, for instance, of this 15 grams of this substance, how much of that is chlorine? That is still composition stoichiometry because you haven't changed anything yet. You're still dealing with this same compound. So what we do here in chapter 9 then, that's why we said you need to have places to stop. No offense, okay? So what you studied in chapter 3 deals with the mass relationships of elements in compounds. Reaction stoichiometry involves the mass relationships between reactants and products in a chemical reaction. Reaction stoichiometry is the subject of this area, or is the subject of this chapter, and is based on chemical equations and the law of conservation of mass. All reaction stoichiometry calculations start with a balanced chemical equation. That's the white paper that was handed back to you. That's where I suppose you could say where we ended last semester was balancing chemical reactions, okay? And then, so then this equation gives a relative numbers of moles of reactants and products. Now, you might be asking yourself, I thought we were talking about masses of substances. Well, in these balanced chemical reactions, it's where you're using the moles as counting units, okay? So that's why we say the equation gives the relative numbers of moles of reactants and products. So how this would change with what we've learned before is, so keep in mind, if we want to know how much chlorine was in there, we would say for every mole of calcium chloride, we want to find the a mass of chlorine to begin to end with. But this third step is still really important. So from last semester, what is the importance of that third step? Good, you're writing it down. Really?
Write it in.
Okay.
For how we can do that,
So for every mole of calcium chloride, we get, is it just a mole of chlorine? Now, this is where it gets to be important, especially in stoichiometry, okay? One of the things that we had told you, okay, is we would go back to our original equation here, okay? And why would we put a 2 there? Because there's 2 chlorines in this formula, so that's why we would put that 2 there, and this is just for good practice. This is still composition stoichiometry, okay? So all of these have canceled. We're in moles of chlorine. So now for every mole of chlorine, get 35.45 grams, okay? Then there's only one step further that we could have taken this is what is the percentage of chlorine in 15 grams of calcium chloride, okay? Again, this is composition stoichiometry. How that is different is, this is where we're going to get further down the road, is if we have calcium, here's our calcium chloride, okay? Now, before you say anything, this equation might be right or it might be wrong. It is wrong right now. Okay? So even though the majority of the time it's just going to be human nature, okay? If you don't put that 2 there, the next 10 minutes that you put into this is going to be all wrong. Worthless is right, okay? So, yes, it's attention to detail with this, all right? So how this is different from what we have learned is, let's say, for instance, if we produce 15 grams of calcium chloride, how many moles of this is needed to do that? Okay? This is how it's different, because not only do you have a chemical reaction, but you got to get from this side of the equation over to that side. Now you're doing reaction stoichiometry, okay? Which, for those of you 1 and 2 years from now, I always call it, this is the entire backbone of what general chemistry is. Everything branches off of this. Everything that you've learned up to this point, okay? Maybe not so much this, but when we look at chlorine, for instance, we could break that down all the way to this good stuff, right?
Oh, yeah.
So that's what I mean. This is using all of the information that you've learned last semester and applying it to this content here, okay? Then the last thing we'd have to do is just balance this, but it's just a coincidence that it's already balanced, correct?
Yes.
Which it would not have been should you have left that alone. Because one of the things that happens is if you forgot that, then you get into a problem, you're going to be off by a factor of 2. And you might say, well, so what if I forgot a 2? Okay, well, I want to borrow you $250 anytime you want it. Because what you're saying is you're going to pay me back $500. I really like that percentage rate. That's 100%. Heck, I can even do that math. Yeah. So balancing chemical reactions is really important. Okay. So because even if you get this right, and if you're just off by a little bit, that's the math that maybe you added something together wrong. Okay, that happens. But forgetting this, that's where problems are really going to probably show or rear their ugly faces, if you want to call that. I think that's one way you can look at it. Okay, but mistakes happen. Okay, for those of you who've been around, well, you're juniors and seniors, we always say 2 things about mistakes. 1, no. We'll go with no. Okay, try not to repeat them. And then 2, try to learn from them, okay? And I don't know if it has to go in that order. I just say it in that order. But again, you're going to make mistakes. But with the exception of up against that wall and up against this wall, and right here, we say look left, look right. There's someone there to pick you up, dust you off, and keep moving forward. Okay. So, reaction stoichiometry problems. Okay? The reaction stoichiometry problem in this chapter can be classified according to the information. We don't have to do this. Just one of the things I have done before, we'll just throw it on the Science Channel and just say you're on your own. You're still getting the content. And that works too. But just let me get through this content and then we'll be done. Okay? The given and the unknown may both be reactants. They may both be products, or one may be a reactant and the other a product. Okay? The masses are generally expressed in grams, but you will encounter both large-scale and micro-scale problems with other mass units such as kilograms, or we don't do milligrams. Now, that might be a little more important if you are a nursing student, okay? Because one of the things that happens is if you're going to be a registered nurse, okay, I always just use the same example because I think it's an applicable one, okay? Who's our doc in here? Okay? So who's the nurse in here? No, but no, who's the nurse? Okay, so the doctor's orders say, let's say, how would that be? 2 scripts of albuterol every 4 hours. Okay, and that could be something as vague as our nurse here, which the doc prescribed. You probably can't read it because that's how doctor's writing is. But if it was your sister, I would say that's probably pretty accurate because I got to put these on so I can read it. Okay, because it's so small. Just ask her classmates. You know that too? Well, you should. You're her sister. Okay. So now the nurse, I'm just going to walk up to the tray and pull out my albuterol for the patient and then just give him this 2 scripts. I don't know if scripts is an actual term. I'm just using it as an example. But 2 scripts is not the concentrated form. You have to go through and mathematically do the dilutions. You just don't walk up to the cabinet and pull that out and then give to the patient. Because it's probably going to be given in maybe deciliters per gram. It could be in milligrams where we're learning grams. That's just one of the things that this hopefully helps some of you categorize things and do this problem solving skills. So thanks, Doc. Okay?
Hey, what's up, Doc?
All right.
Yeah, Arian. What's up, Doc?
Stoichiometric problems are solved by using ratios from the balanced equation to convert the given quantity using the methods described here. Now, to me, yes, it tells you what to do in the problem, okay? But to me, I really think it's more beneficial just to see the example. Then you can administer that. Like, for instance, let's see here. I'm going to pick on the back row. I'm thinking combination headlock, takedown, and reverse. Of course, you can try to describe that to someone who doesn't know anything about wrestling, which would be myself. But what's a better way than trying to describe it? Just showing them that. So this is kind of like, no offense, but if you're trying to describe what I said, which I don't even know if is a real thing either, but what would be better? For you to describe it or to show them? You're not just agreeing. You agree that showing would be better? Okay. So let's go ahead and turn the page then. And there again, what you see with the mole ratio, are we like playing handsy or something over here, or do we need to split you up or
I
what?
like to watch his brain melt sometimes. It is currently happening.
Okay, well, we're a little bit behind right now. Okay, the mole ratio. Okay, solving any reaction stoichiometry problem requires the use of a mole ratio to convert from moles or grams of one substance in a reaction to moles or grams of another substance. A mole ratio is a conversion factor that relates the amounts in moles of any two substances involved in a chemical reaction. This information is obtained directly from the balanced chemical equation. Consider, for example, the chemical equation for the electrolysis of melted aluminum oxide to produce aluminum and oxygen. So a lot of the things that we mine out of the earth, you just don't take copper out of the earth. You just don't take iron out of the earth. You don't take aluminum. Yes, it's found in the earth, but that's not the raw form. The raw form would mean you have to, let's say, not just after mine it, but you have to refine it, just like crude oil. So when you take this mineral ore, whether it's iron, copper, aluminum, if it's mixed with other substances, once you refine it, you break it apart into its raw forms, just like what we're doing here, aluminum and oxygen. So upon doing that, that's why you see with that balanced chemical equation, okay? For instance, even if you didn't have that, I would expect that you would be able to balance this chemical reaction. So we can do something very similar. Let's say, for instance, if we had, we'll keep it really simple. We'll just do a decomposition reaction. Okay? So if this is a decomposition reaction, what's taking place on that side? What happens when things decompose? Okay? So when we say they split, which they do, okay? Okay, here again, if you do not put this little number here, anything you do beyond that is probably going to be wrong. Okay? So upon doing that, we have to balance that. We got 2 there and then 2 there. Okay? Do we have anybody who really likes working with metal and welding metal? Nobody? So I could just make this up and you wouldn't know if I'm right or not, which is what we do all the time. You just don't know if it's right. Does it just sound pretty good? Must be pretty convincing. I should have been a politician. Yeah, these knuckleheads in Washington can't get their stuff in a group. But anyway, so with that, okay, if you're working with a metal that has magnesium in it, okay, which it could be anything from, let's say, as simple as a rake, or maybe something as simple that could be on the chassis of a truck or a tractor or something like that. If you have to, let's say, do some welding on that, heat is a really good catalyst, and if this is in that substance, okay, it's really tough to work with because that heat is going to break these apart. And once that happens, what's actually happening in welding if you're stick welding? You're sending large amounts of electricity through, it's called arc welding, right? So it's sending it through, okay, through the stick or that rod, those large amounts of electricity. And what it's doing is it's melting the metal as you go because it's just that hot, okay? So this heat is breaking this substance apart, but look at what one of the byproducts is here. It's really tough to work with because that oxygen keeps breaking down from the magnesium oxide, and you get spontaneous flames all the time. Okay? So something as simple as that can explain why this substance is really, really tough to work with. Okay.
Bro, tear the top. We got those this morning.
Go ahead and tear the top.
No, don't let him touch my stuff.
Thought for sure it was going to go flying all over. No offense. But thank you for doing that. Because I'm not going to lie, that was really, really annoying. Okay? Anyway, so what we can presume here is what they're illustrating on page 300. Okay? If we have to jump from one side of the equation to the other, okay, like what we do here, okay, this mole ratio is saying we've got 2 moles of magnesium oxide. For how many moles of oxygen do we have? How many moles of oxygen? How many moles of oxygen? See, this is where we got to make that transition from last semester to this semester now. Okay? Because you're getting that 2 from this guy, right? Now, when we're talking about mole ratios, we got to be concerned about these guys now. Okay? They're up front. So that's where that 2 comes from here, and why we don't put anything here, because there's a 1 there. The reason that we had you put that 2 there last semester was so that you didn't forget to multiply that by 2. So your thinking is just that we're changing it just a little bit for your benefit. Okay. So one of the things, the last thing we'll say is when we look at this is these mole ratios, it's just, again, a way of counting. If when you're looking at feet, for instance, okay, the simplest way for me to describe this desk here, I don't want to be dealing with 96 inches all the time as far as a measurement. What would be a much simpler conversion from 96 inches to get a smaller number? You know the answer, you just don't know you know it. Because I think someone just said it. Say that again. I thought you did. Feet. But how many feet? 8 feet. 96 inches is 8 feet. 62 inches then puts you at 6 feet. Okay? So that's what a mole ratio is. It's just an easier way of dealing with smaller numbers rather than larger ones. Okay? Because again, I don't want to be dealing, if we have to cut this in half, yeah, you would say it's 48 inches, but cutting it at 4 feet is a lot simpler than saying, well, I want to do it at 48 inches. Okay. All right, so tomorrow, grab your books again every day, and we will start doing some of these stoichiometry calculations. All right, that's all I have. We'll catch up to you next time.